Look up at the night sky. What do you see? Stars, planets, maybe a distant galaxy if you're lucky. But here's the astonishing truth. Everything visible to us, everything we've ever observed with telescopes or satellites, makes up less than 5% of the universe. The rest, a cosmic enigma, hidden in plain sight. 95% of reality is composed of dark matter and dark energy, two mysterious forces that shape the cosmos yet remain utterly invisible to our eyes. We're living in a universe where the majority of what exists is completely unknown to us. It's like standing in a room where you can only see the furniture, but not the walls, the floor, or even the air you're breathing. This isn't just a gap in our knowledge, it's a fundamental puzzle that redefines how we understand existence itself. Dark matter's gravitational pull holds galaxies together, while dark energy drives the universe to expand at an accelerating rate, pushing galaxies apart with incomprehensible force. Yet, despite their overwhelming presence, we've never directly detected them. They're the universe's dark backbones, the unseen scaffolding upon which everything we know is built. And the deeper we look, the stranger it gets. Unexplained gravitational ripples, cosmic voids where matter seems to vanish, and galaxies that move in ways they shouldn't. All of these point to a reality far more bizarre than we ever imagined. That's where our journey begins. In this video, we're diving into 34 of the most cutting-edge explorations of these vast unknowns, from the latest theories about dark matter's elusive nature to the mind-bending experiments trying to uncover dark energy's secrets. We'll travel to the edges of astrophysics, where researchers are peeling back the layers of the cosmos, only to find more questions waiting beneath. Why do galaxies rotate as if gripped by invisible hands? What lurks in the emptiness between stars, defying the laws of physics as we know them? Every discovery we make doesn't just answer old mysteries. It opens doors to new ones, revealing a universe that's stranger, grander, and more mysterious than we ever dared to dream. So, are you ready to step into the unknown? Let's begin. Imagine a sculptor shaping clay without ever touching it, an invisible force molding galaxies into spirals, clusters, and vast cosmic webs. That's the power of dark matter. Though we can't see it, feel it, or even detect it directly, its gravitational grip is the reason galaxies don't fly apart as they spin. Think of it like the wind. You don't see it, but you see its effects in the sway of trees or the ripple of waves. Dark matter works the same way, bending light from distant stars and holding galaxies together with an unseen hand. Scientists calculate that dark matter makes up roughly 27% of the universe, outnumbering ordinary matter, the stuff we're made of, by more than 5 to 1. Yet, despite its overwhelming presence, we still don't know what it is. The search for answers has led to some of the most ambitious experiments in history. Beneath the Swiss-French border, the Large Hadron Collider smashes particles together at nearly the speed of light, hoping to create dark matter in miniature. Meanwhile, telescopes like the Hubble and the upcoming Nancy Grace Roman Space Telescope scan the deepest corners of space, mapping the way dark matter distorts the fabric of reality itself. Theories abound about what dark matter could be. Some researchers think it might be WIMP, weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Others propose actions, ultra-light particles that could flow through the cosmos like an invisible river. Then there's the wilder idea: could dark matter be evidence of an entirely separate universe, a shadow realm existing alongside ours, forever out of reach? Every experiment, every observation brings us closer to an answer, but also deeper into the mystery. When galaxies move in ways that defy gravity's known rules, when cosmic structures form faster than they should, dark matter is the prime suspect. Yet it remains the universe's most frustratingly elusive architect. The hunt isn't just about solving a scientific puzzle, it's about rewriting our understanding of reality. Because if dark matter isn't what we think, then everything we know about the cosmos might just be the tip of the iceberg. If dark matter is the invisible glue holding galaxies together, dark energy is its polar opposite, the unseen force relentlessly pushing the universe apart. Picture blowing up a balloon with galaxies drawn on its surface, but instead of slowing down as it expands, the balloon inflates faster and faster, stretching those galaxies away from each other at speeds that defy explanation. That's the bizarre reality we're facing. In the late 1990s, astronomers studying distant supernova made a shocking discovery. The universe's expansion wasn't slowing down due to gravity, as everyone expected. It was accelerating, as if some mysterious energy were working against gravity's pull. This invisible driver, dubbed dark energy, now makes up a staggering 68% of the universe's total energy. Unlike dark matter, which tugs matter together, dark energy seems to be woven into the fabric of space itself, growing stronger as the cosmos expands. Einstein once proposed a similar idea, his cosmological constant, but even he dismissed it as his greatest blunder. Now, it's back in play as one possible explanation for dark energy, a constant, unchanging force embedded in empty space. But what if it's not constant at all? Some theories suggest dark energy could evolve over time, growing stronger or weaker in ways that would reshape the universe's ultimate fate. To unravel this mystery, projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are mapping billions of galaxies, measuring how their light bends and fades as dark energy stretches the space between them. The results so far only deepen the enigma. If dark energy strengthens, it could eventually tear apart galaxies, stars, and even atoms in a catastrophic Big Rip. If it weakens, the universe might collapse back on itself in a big crunch. Or perhaps it's something entirely stranger, a sign of undiscovered physics, a fifth fundamental force, or even evidence of hidden dimensions. The more we probe dark energy, the more it challenges our understanding of reality. Why does empty space have energy at all? How does it push the universe apart without any detectable source? These aren't just academic questions, they're clues to the universe's ultimate destiny. And right now, every observation, every calculation brings us face to face with the humbling truth. We're only beginning to grasp the forces shaping existence itself. Some of the most compelling proof for dark matter comes not from what we can see, but from what we can't. Take the Bullet Cluster, one of the most dramatic cosmic collisions ever observed. Here, two galaxy clusters slammed into each other at millions of miles per hour, a wreck so violent it should have left chaos in its wake. But instead of confusion, this collision revealed something extraordinary. When astronomers studied the aftermath, they found that most of the mass, the real gravitational heavyweight, wasn't where the visible matter ended up. The stars and gas, slowed by friction, lagged behind, yet something invisible had sailed straight through the chaos, dragging the fabric of spacetime with it. How do we know? Einstein's theory of general relativity gave us the tool, gravitational lensing. Just as a magnifying glass bends light, massive objects warp space, distorting the light from galaxies behind them. In the Bullet Cluster, the invisible mass dark matter bent light in ways normal matter couldn't explain. It was the first time we'd essentially mapped dark matter's presence, not by seeing it, but by seeing its shadow. This wasn't just a theory anymore. Dark matter had left its fingerprints on the cosmos, but the bullet cluster is more than proof, it's a clue. If dark matter barely interacts with normal matter, even in a collision of this scale, what does that tell us? It suggests dark matter might be something far stranger than just undiscovered particles. Some researchers wonder if it could be evidence of extra dimensions or even a parallel universe brushing against ours. Meanwhile, other cosmic smash-ups like the musket ball cluster or the baby bullet show similar patterns, reinforcing the idea that dark matter isn't just a fluke, it's everywhere, shaping the universe while remaining frustratingly out of reach. The hunt for answers has taken scientists to some of the most extreme environments in space. Colliding galaxy clusters act like natural laboratories, revealing dark matter's behavior in ways no experiment on Earth can replicate. Each new discovery peels back another layer, showing us where dark matter isn't, and forcing us to ask with even greater urgency where it might be hiding. Because if something this massive, this pervasive, can stay invisible, what else might we be missing? There's something out there, something massive, invisible, and pulling us toward it at over 600 kilometers per second. Hidden behind the thick dust and stars of our own Milky Way lies one of the universe's most baffling mysteries, the Great Attractor. This colossal gravitational anomaly acts like a cosmic magnet, dragging not just our galaxy but thousands of others toward it with irresistible force. For decades, its true nature remained obscured by what astronomers call the zone of avoidance, a region of space so dense with interstellar dust and gas that traditional telescopes couldn't penetrate it. It's like trying to peer through a fogged-up window while hurtling toward whatever's on the other side. What could exert such a powerful pull? Early theories suggested it might be a supercluster of galaxies, a dense knot of matter with enough gravity to bend the motion of everything around it. But when scientists finally mapped the region using infrared and radio telescopes that cut through the dust, they found something even more surprising. The Great Attractor wasn't the end of the story, it was just a waypoint. Beyond it lies an even larger structure, the Shapley Supercluster, a staggering collection of galaxies so massive it might be the single largest concentration of matter in our observable universe. Together, these titans of gravity could explain why our cosmic neighborhood is moving so fast. Yet the mystery deepens. Some researchers wonder if the Great Attractor's pull is too strong to be explained by visible matter alone, hinting at hidden reservoirs of dark matter woven into these vast structures. Others speculate about more exotic possibilities. Could there be a flaw in Einstein's theory of gravity on cosmic scales, or even a gravitational echo from another universe tugging at ours? The answer might lie in the next generation of telescopes, like the upcoming Square Kilometre Array, which will scan the zone of avoidance with unprecedented clarity, peeling back the Milky Way's veil to reveal what's really pulling us in. But here's the strangest twist. The Great Attractor isn't just pulling us toward it, it's part of a far grander flow. Galaxies across the universe are drifting like leaves on a river, all moving toward an even more distant and mysterious region known as the Dipole Repeller. This cosmic tug of war between attraction and repulsion paints a picture of the universe as a dynamic, interconnected web, where invisible forces sculpt the paths of galaxies on scales we're only beginning to comprehend. Every new observation reminds us that the cosmos is far from static. It's a living, breathing entity full of motion and mystery, with the Great Attractor as just one piece of an endless puzzle. The universe is expanding, that much we know, but how fast? You'd think measuring something as fundamental as the Hubble constant, the rate of cosmic expansion, would be straightforward. Yet here we are, staring down a full-blown crisis in cosmology. Depending on how you measure it, the universe's expansion rate gives wildly different answers, like two clocks ticking at different speeds, each insisting it's right. This discrepancy, known as the Hubble tension, isn't just a minor hiccup. It's a flashing red light that our understanding of the cosmos might be missing something profound. One method relies on the cosmic microwave background, the afterglow of the Big Bang. By studying its faint ripples with missions like Planck, scientists calculate an expansion rate of about 67 kilometers per second per megaparsec. That's the universe's speed limit according to the early cosmos. But then we have the local measurements, where astronomers track the distances and movements of nearby stars and supernova. These observations, led by the Hubble Space Telescope, peg the expansion closer to 73. That might not sound like much, but in the precise world of cosmology, a gap this big screams that something's off. It's like trying to bake a cake with two different recipes, one insisting on more flour, the other on less, and no one can figure out why. So what's causing the mismatch? Some theorists argue we might be underestimating dark energy's quirks. Maybe it's not a constant force, but one that evolves, growing stronger or weaker over time. Others wonder if there's an unknown particle, a dark radiation, subtly altering the early universe's behavior. Then there's the radical possibility. What if gravity itself works differently on cosmic scales, bending the rules in ways Einstein never predicted? The tension isn't just a math error. It's a signpost pointing to gaps in our knowledge, gaps that could hide entirely new physics. Efforts to resolve the conflict are pushing technology to its limits. The James Webb Space Telescope is now double-checking Hubble's local measurements with unprecedented precision, while next-generation observatories like the Vera Rubin Telescope will map billions of galaxies to cross-examine the cosmic microwave background. The stakes couldn't be higher. If the tension holds, it could mean rewriting textbooks, dethroning long-held theories, or even uncovering a fifth fundamental force. But if it vanishes, we'll have to ask an even more unsettling question. Were we wrong about being wrong? Either way, the Hubble tension isn't just a problem, it's an invitation. The universe is handing us a puzzle, and solving it might just reveal the next chapter in the story of everything. One moment, the universe is silent. The next, a flash of radio waves brighter than 500 million suns erupts from the void, vanishing almost as quickly as it appeared. These are fast radio bursts, cosmic fireworks so powerful they outshine entire galaxies, yet so fleeting we almost missed them entirely. First discovered in 2007, these bizarre signals last just milliseconds, but in that blink of an eye, they release enough energy to dwarf our sun's output for decades. And the strangest part, we still don't know what's causing them. Take FRB 121102, the first repeating fast radio burst ever detected. Unlike one-off bursts, this one sends signals in unpredictable patterns, like a cosmic Morse code with no clear sender. At first, astronomers thought collapsing neutron stars or colliding black holes might explain these bursts' violent, one-time events, but repeaters like 121102 shattered that idea. Now, theories range from magnetars, highly magnetic neutron stars with eruptions powerful enough to rip spacetime, to something even more speculative. Could these be artificial? Some scientists have dared to ask if advanced civilizations might be behind them, using unimaginably powerful transmitters to communicate, or even propel ships across galaxies. The hunt for answers is accelerating. Telescopes like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, scan the sky daily, catching hundreds of these bursts and tracing their origins to distant galaxies billions of light years away. Each detection adds a new piece to the puzzle. Some bursts twist their radio waves in ways that suggest they've traveled through incredibly dense magnetic fields, pointing to extreme environments like the outskirts of supermassive black holes. Others arrive with a crisp, clean signal, as if they've barely interacted with anything on their journey through the cosmos. What's truly mind-bending is the scale of these events. A single fast radio burst can outshine every star in its host galaxy combined, yet it leaves no visible trace, no light, no heat, just a ripple in the radio spectrum. It's like hearing an explosion in a pitch-black room and never finding the source. And with new bursts being detected almost weekly, each one seems to defy expectations. Some come with a side of X-rays or gamma rays, while others are radio only, as if the universe is teasing us with clues but refusing to reveal the full picture. The implications are staggering. If these bursts are natural, they could be windows into the most extreme physics in the universe, environments where matter is crushed into bizarre states we can't replicate on Earth. If they're artificial, well, that opens a door to possibilities far beyond our current understanding. For now, fast radio bursts remain one of space's most electrifying mysteries, a reminder that even in the silent stretches between stars, the cosmos is anything but quiet. Every new detection isn't just a signal, it's a question waiting for an answer. Beyond Neptune, where sunlight is a faint memory and temperatures plunge near absolute zero, the Kuiper belt holds a cosmic secret, objects moving in ways that defy logic. Take Sedna, a dwarf planet with an orbit so stretched it takes 11,000 years to circle the Sun, swinging from 76 times Earth's distance to nearly 1,000. It's not alone. Dozens of icy bodies out here trace similarly bizarre paths, clustering in tilted, elongated orbits as if guided by an unseen hand. The math doesn't lie. Something massive, perhaps 5 to 10 times Earth's size, could be warping these orbits from the shadows. Astronomers call it Planet 9, a hypothetical super-Earth lurking so far out it could take 20,000 years to complete a single trip around the Sun. Simulations show its gravitational pull neatly explains the Kuiper belt's oddball orbits, shepherding objects like a cosmic puppeteer. Yet, despite years of searching, we've found no direct evidence. Is it a ghost planet, or are we missing something even stranger? The hunt has turned into a high-stakes game of celestial hide and seek. Telescopes like Subaru on Mauna Kea scan the outer solar system for faint glimmers, while researchers track the peculiar motions of distant objects for clues. Every new discovery, like the ultra-distant Goblin or the highly tilted Biden, tightens the noose around Planet 9's possible location, but alternatives exist. Could a primordial black hole, no larger than a grapefruit but as massive as a planet, be warping orbits instead? Or might the anomalies stem from a passing star's ancient gravitational nudge, frozen in time? What's clear is this: the Kuiper belt is more than a relic of the solar system's birth. It's a dynamic frontier where known physics meets mystery. Whether the culprit is a hidden planet, a rogue black hole, or something entirely unforeseen, the answer will rewrite our understanding of home. Because if we're still discovering worlds in our own backyard, imagine what else lies in the darkness waiting. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many of which host planets in the so-called Goldilocks zone, where conditions are just right for life. Statistically, it seems inevitable that we should have neighbors out there. Yet when we point our telescopes and listen for signals, all we hear is silence. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If intelligent life is common, why haven't we found a single trace of it?" One unsettling possibility is that advanced civilizations tend to self-destruct before they can spread across the cosmos. Nuclear war, runaway climate change, or unchecked artificial intelligence could act as great filters, wiping out civilizations just as they reach the technological stage where interstellar communication becomes possible. If this is true, humanity's silence might be a warning, a cosmic cautionary tale written in the stars. But not all theories are so grim. Some suggest that intelligent life might be deliberately avoiding us, either out of caution or disinterest. Imagine an ant hill in the middle of a highway. The ants might never notice the cars speeding past, and the drivers certainly wouldn't stop to chat. Could we be the ants, oblivious to civilizations so advanced that we're beneath their notice? Or perhaps they've developed stealth technologies far beyond our detection, rendering their presence invisible to our primitive instruments. Then there's the zoo hypothesis, the idea that Earth is deliberately left untouched, a protected wildlife reserve in a galaxy teeming with life. It's a thought both comforting and isolating. We might not be alone, but we're intentionally kept in the dark. Meanwhile, projects like Breakthrough scan millions of stars for artificial signals, hoping to catch even a whisper of extraterrestrial intelligence. So far, the silence is deafening. The paradox deepens when we consider just how young we are in cosmic terms. The universe is 13.8 billion years old, while human civilization has existed for a mere blink of that time. It's possible that other civilizations rose and fell billions of years before us, leaving behind ruins we've yet to discover. Or maybe we're among the first, with the bulk of intelligent life still to come. Whatever the answer, the Fermi Paradox forces us to confront profound questions about our place in the universe. Are we a cosmic fluke, or is the universe hiding its inhabitants in ways we can't yet comprehend? The search continues, and every silent night sky is a reminder the truth is out there waiting to be found. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radiation so intense, so perfectly tuned to the frequency of interstellar hydrogen that the astronomer who found it scrawled, "Wow." In red ink on the printout, for 72 seconds the signal blared 30 times louder than the background noise of space, then vanished without a trace. Decades later, it remains astronomy's most tantalizing maybe, a blip that could have been our first brush with extraterrestrial intelligence, or just a cosmic prank from an unexpected source. The WOW signal had all the hallmarks of an artificial transmission. It appeared near the frequency of 1420 MHz, the natural vibration of hydrogen, the universe's most abundant element, precisely the channel an advanced civilization might use to announce itself. It was narrowband, meaning it occupied a slim slice of the radio spectrum, unlike natural cosmic noise, and it came from the direction of Sagittarius, a star-rich region where the odds of life seemed higher. Yet despite countless follow-up searches, including projects like SETI-dedicated scans of the same patch of sky, the signal never repeated. It was as if the universe whispered hello, then slipped back into silence. So what was it? Skeptics point to more mundane explanations. In 2017, researchers proposed it might have been a comet. Two icy bodies, 266P and 335P, were passing through that region at the time, their hydrogen clouds potentially reflecting sunlight in a way that mimicked a radio burst. But critics note the signal's characteristics don't quite match known comet behavior, and the telescope's design made it unlikely to mistake a reflected signal for something so intense. Others wonder if it was a military transmission, a satellite glitch, or even an echo from some long-forgotten human-made probe. Then there's the electrifying possibility: what if it really was them? The WOW signal fits the profile of an intentional beacon, a deliberate ping across the cosmic ocean. If so, why haven't we heard it again? Maybe the sender assumed we'd reply promptly, and when we didn't, moved on. Or perhaps the signal was never meant for us at all, just a stray fragment of some distant civilization's internal chatter, briefly brushing past Earth like a ship's light glimpsed through fog. The mystery endures because it sits at the edge of what science can confirm. Without repetition, the signal slips into legend, a Rorschach test for our hopes and doubts about life beyond Earth. But the hunt isn't over. Newer telescopes armed with AI to sift through radio noise in real time scan the skies for another whisper like wow, something too strange to ignore, too precise to dismiss. Until then, those 72 seconds remain frozen in time, a question mark written in the static of the cosmos. Was it a comet's fleeting cry, a blip in the machine, or the moment we first heard a voice not our own? The universe isn't telling yet, stretching across the cosmic microwave background like a shadowy fingerprint. The cold spot is one of the universe's most perplexing anomalies. This vast, chilly region, spanning nearly 2 billion light-years, is significantly colder than its surroundings, a cosmic bruise that defies easy explanation. When scientists first mapped the afterglow of the Big Bang, they expected minor fluctuations, tiny ripples in temperature reflecting the universe's infant structure. But the cold spot wasn't just a ripple, it was a tidal wave, a deviation so extreme that its odds of appearing by random chance are less than 1 in 50. So what carved this frigid void into the fabric of spacetime? One radical theory suggests it might be a collision scar, evidence of our universe brushing against another in the multiverse. Imagine two soap bubbles floating in a froth of higher dimensional space. Where they graze each other, energy could leak between them, leaving a cold, stretched patch on each bubble's surface. If true, the cold spot might be our first tangible clue that other universes exist beyond our own, a cosmic handshake frozen in time. Not everyone is convinced, of course. Skeptics argue the cold spot could simply be a statistical fluke, a trick of perspective caused by a vast, sparsely populated supervoid, a region where galaxies are suspiciously scarce. Light traveling through such a void would lose energy, stretching into longer, cooler wavelengths, a phenomenon known as the integrated Sachs-Wolf effect. But even this explanation has holes. The supervoid needed to produce the cold spot's temperature drop would have to be impossibly large, far exceeding any known structure in the universe. The debate has sparked a race to uncover the truth. Telescopes like the Atacama Cosmology telescope scrutinize the cold spot structure, hunting for patterns that could reveal its origins. Meanwhile, simulations of multiverse collisions predict specific signatures, subtle distortions in the cosmic microwave background's polarization that future observatories could test. The stakes are astronomical. If the cold spot is indeed a multiverse relic, it would upend our understanding of reality, proving we're just one universe among countless others, each with its own laws of physics. But here's the twist: even if it's just a supervoid, its sheer size challenges our models of cosmic structure. How did such a vast emptiness form? What does it tell us about dark energy's role in sculpting the universe? The cold spot isn't just a scientific puzzle, it's a mirror, reflecting back the limits of our knowledge. Whether it's a window to the multiverse or a cosmic oddity, one thing's certain: the universe is still full of surprises, and the cold spot might just be the coldest and most thrilling clue we've ever found. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself. According to Stephen Hawking's groundbreaking work, these gravitational monsters don't just swallow matter, they erase information from the universe, atom by atom. Here's the problem: quantum mechanics insists that information can never truly be destroyed. It might get scrambled, hidden, or transformed, but it should always exist in some form. Yet Hawking radiation, the faint glow of particles leaking from black holes, appears to carry no trace of what fell in. It's like burning a library and claiming the smoke contains every word from every book, except the smoke is just random thermal noise. This clash between quantum theory and general relativity is the black hole information paradox, and solving it could rewrite the laws of physics. At the heart of the paradox is a question with existential stakes. What happens to the identity of particles when they cross a black hole's event horizon? Imagine tossing a chair into a black hole. Quantum mechanics says the chair's information, its shape, material, even the scratches on its legs must persist somehow. But Hawking radiation suggests that after the black hole evaporates, only featureless energy remains. No chair, no scratches, no history. This isn't just about furniture, it's about whether the universe keeps receipts. If black holes truly delete information, then reality has a built-in forgetting mechanism, and quantum physics is fundamentally flawed. Desperate to resolve the paradox, physicists have proposed mind-bending solutions. One idea, the firewall hypothesis, suggests the event horizon isn't a smooth gateway, but a wall of searing energy that vaporizes anything touching it. This would preserve information by destroying incoming matter before it reaches the singularity, but it also violates Einstein's vision of free fall into a black hole as an uneventful plunge. Another approach, holographic theory, argues that information isn't lost but smeared across the black hole's surface like a cosmic etch-a-sketch. In this view, the three-dimensional chair is encoded as a two-dimensional pattern on the event horizon, preserved until the black hole's final moments. The stakes couldn't be higher. If holography is correct, it implies our entire universe might be a projection, with reality's true code written on some distant, invisible surface. Firewalls, meanwhile, demand a rewrite of how spacetime behaves under extreme conditions. Both ideas push the boundaries of known physics, hinting at a deeper theory that could finally unite quantum mechanics and gravity. Recent breakthroughs add fuel to the fire. In 2023, scientists used quantum computers to simulate how information might escape black holes, finding tantalizing clues that Hawking radiation isn't as random as it seems. Meanwhile, telescopes like the Event Horizon Telescope peer at black hole shadows, searching for anomalies that could betray hidden information. Every experiment, every calculation brings us closer to an answer or deeper into the maze. Because if black holes don't play by the rules, what else have we gotten wrong about the universe? The paradox isn't just a puzzle, it's a gateway, and on the other side might lie the keys to the cosmos itself. In October 2017, astronomers spotted an object streaking through our solar system at nearly 200,000 miles per hour, but this was no ordinary asteroid. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from interstellar space, a tumbling, cigar-shaped enigma that defied all expectations. What made it truly bizarre wasn't just its origin, it was how it moved. Instead of slowing down as it passed the sun, as gravity dictated, Oumuamua sped up as if pushed by an unseen force. At first, scientists scrambled to explain it with natural causes. Maybe Oumuamua was a hydrogen iceberg, vaporizing in sunlight like a cosmic comet, its invisible jets giving it a kick. But hydrogen ice is fragile, it shouldn't survive the heat of interstellar travel. Others suggested it was a nitrogen iceberg, chipped off a Pluto-like exoplanet. Yet no telescope caught even a whiff of gas or dust trailing behind it, something even the most sterile comets produce. The more we studied Oumuamua, the weirder it got. Its shape, possibly 10 times longer than it was wide, was unlike any known asteroid. Its brightness varied wildly as it tumbled, suggesting an irregular, almost metallic surface. And then there was that acceleration, precise and steady, as if guided. That's when the speculation turned extraordinary. Harvard astrophysicist Avi Loeb proposed a radical idea. What if Oumuamua wasn't a rock at all, but a light sail? An artificial object propelled by starlight, perhaps a discarded piece of alien technology. The theory ignited fierce debate. Critics argued it was classic aliens of the gaps, invoking extraterrestrials whenever nature stumps us. But Loeb countered that science shouldn't dismiss possibilities just because they sound like science fiction. After all, humanity's own light sail, the Breakthrough Starshot project, aims to send tiny probes to Alpha Centauri using the same principle. Could Oumuamua have been someone else's starshot, long adrift? The truth is, we may never know. By the time we spotted Oumuamua, it was already racing out of the solar system, too distant for further study. Future telescopes like the Vera Rubin Observatory will scan for more interstellar visitors, hoping to catch them earlier. But Oumuamua remains a tantalizing what-if, a cosmic postcard we barely had time to read before it vanished into the dark. Whether it was a shard of an alien world or something even more extraordinary, its fleeting visit reminds us the universe is full of travelers, and some might not be passing by accident. Picture the universe as a vast ocean with galaxies bobbing like boats on its surface. Most drift apart as the cosmic tide of dark energy pushes space itself outward. But something strange is happening in the deep. Entire clusters of galaxies, thousands of them, are moving together in the same direction at breakneck speeds, as if caught in a current invisible to our telescopes. Astronomers call this the dark flow, and it's one of the most unsettling mysteries in modern cosmology. These aren't random motions. They're coordinated, precise, all streaming toward a single patch of sky near the constellations Centaurus and Vela, as if something out there, something beyond the edge of everything we can see, is pulling them. The dark flow was discovered by accident. While studying the cosmic microwave background, scientists noticed something odd. The afterglow of the Big Bang showed subtle temperature shifts in the direction of these moving galaxy clusters. As clusters race toward us, their motion squeezes light waves slightly, making the cosmic microwave background appear warmer in front of them and cooler behind. But when researchers mapped these shifts, they found clusters moving at speeds up to 2 million miles per hour, far faster than the universe's expansion should allow. Even stranger, the flow extends at least 3 billion light-years, a distance so vast it defies conventional explanations. What could possibly exert such a titanic pull? One radical idea points to gravity leaking from other dimensions. In string theory, our universe might float like a membrane in higher dimensional space, with nearby, branes, parallel universes tugging on ours from realms we can't perceive. If a massive structure in a neighboring brane lies beyond our cosmic horizon, its gravity might be warping our universe's fabric, dragging galaxies along like iron filings to a magnet. Then there's the super-universe hypothesis. If our cosmos is just one bubble in an infinite multiverse, what's to say there aren't other, far larger bubbles beyond our observational limits? A colossal structure in this super-universe, something so immense it makes our entire visible cosmos look like a speck, could be yanking galaxies toward it with gravitational force we can't directly detect. Skeptics argue the dark flow might be an illusion, a statistical fluke, or an error in interpreting cosmic microwave data, but the evidence keeps mounting. In 2023, a study of over 1,000 galaxy clusters confirmed the flow's persistence, with some clusters moving in sync across distances that should make coordination impossible under standard cosmology. If dark energy is supposed to drive galaxies apart, why are so many racing in the same direction? The implications are staggering. If the dark flow is real, it means our universe isn't just expanding, it's being pulled. The cosmic map we've relied on for decades might be missing entire continents of reality, hidden just beyond sight. Upcoming missions like the Euclid Space Telescope aim to measure the flow's reach with unprecedented precision, hunting for distortions in the cosmic web that could reveal its source. Until then, the dark flow remains a ghostly reminder. The universe is far stranger and far more connected than we ever imagined. Imagine walking into a room expecting a crowd, only to find it eerily empty. Not just empty, but unnervingly vast, with walls so distant they barely seem real. That's the experience astronomers have when they peer into cosmic voids, regions of space so barren they defy comprehension. The Boötes Void, one of the largest known, stretches over 300 million light-years, a gaping hole in the universe's fabric where fewer than 60 galaxies linger. To put that in perspective, a typical chunk of space that size should contain at least 10,000 galaxies. Instead, the Boötes Void is a cosmic desert, a place where matter seems to have vanished without a trace. So how does a void this massive even form? One theory suggests it's a relic of the universe's infancy, a scar left behind by sound waves rippling through the hot plasma of the Big Bang. These primordial vibrations, called Baryon acoustic oscillations, may have pushed matter into dense clusters, leaving behind hollow bubbles in their wake. Think of it like batter settling into a waffle iron. The high spots are galaxy clusters, and the gaps are the voids. But the Boötes Void isn't just a gap, it's a chasm, far emptier than most models predict. Some researchers wonder if dark energy played a role, accelerating the expansion of these regions until they became near-perfect vacuums. Then there's the unsettling silence. Galaxies in the Boötes Void aren't just sparse, they're oddly isolated, with few neighbors to interact with. In a universe where galaxies tend to cluster like fireflies in a summer field, these loners drift in darkness, their stars burning with no one to witness them. The void's sheer scale raises spine-tingling questions. Did something prevent matter from gathering here, or was it deliberately cleared out? Could there be forces at work we haven't yet imagined, sculpting the cosmos on scales we're only beginning to map? Voids aren't just empty space, they're active players in the universe's evolution. Their gravitational pull tugs on surrounding galaxies, subtly shaping the cosmic web. Some simulations even suggest voids might be growing, their boundaries stretching as dark energy pushes the universe apart. Future telescopes like the Nancy Grace Roman Space Telescope will probe these desolate regions, hunting for faint galaxies or traces of hidden matter that might explain their existence. Until then, the Boötes Void remains a haunting reminder. In a universe teeming with light and motion, some corners are content to stay silent, guarding their secrets in the dark. The cosmic microwave background should be the universe's most democratic feature, a near-perfect snapshot of the Big Bang's afterglow, indifferent to where or how we observe it. But when scientists mapped its subtle temperature variations, they stumbled upon something unsettling. The cosmos appears to have a preferred direction. Dubbed the axis of evil, this eerie alignment shows the CMB's fluctuations curiously mirroring the plane of our solar system, as if the universe itself is tipping its hat to Earth. That shouldn't happen in a truly isotropic universe, one without any special axes or directions. Such a pattern would be as likely as flipping a coin 100 times and getting heads every single time. At first, researchers dismissed it as a fluke, a trick of measurement or statistical noise. But as data poured in from missions like Planck and WMAP, the anomaly refused to vanish. The axis of evil isn't just a faint whisper in the data, It's a shout, with odds of occurring by chance estimated at less than 1 in 10,000. If the universe were a classroom, this would be like every student somehow turning their desks to face the same corner for no apparent reason. The implications are profound. Either our cosmological models are missing a critical piece, or we're seeing the universe through a distorted lens, one that's subtly warped by our own celestial neighborhood. One possibility is that the solar system's motion is imprinting itself on the CMB. As we hurtle through space at over 600 kilometers per second, the Doppler effect could stretch and squeeze the microwave background, creating false patterns. But calculations show this can't fully explain the axis's scale or persistence. Another theory suggests an undiscovered foreground object, perhaps a colossal structure of dust or gas, might be casting a shadow on the CMB, like a cosmic hand blocking part of a flashlight's beam. Yet no such structure has been found, leaving the anomaly stubbornly intact. Then there's the radical alternative. What if the universe isn't uniform at all? Cosmology's bedrock principle, the cosmological principle, states that the universe should look roughly the same in every direction on large scales. But the axis of evil hints at a cosmos with a grain, like wood, where properties change depending on which way you look. If true, it would mean the universe has a texture, a structure that privileges certain directions over others, an idea that upends centuries of astronomical thought. The most unsettling explanation of all, we might be seeing evidence of a pre-Big Bang universe. Some theories propose that our cosmos was born from the collapse or collision of a prior reality, leaving behind scars in the CMB. The axis of evil could be one such scar, a fossilized imprint of a time before time. Until we unravel this mystery, it stands as a humbling reminder: the universe doesn't owe us symmetry. And sometimes the most profound discoveries begin with a pattern that simply refuses to make sense. In the vast emptiness between planets, where the sun's grip weakens to little more than a whisper, two spacecraft named Pioneer 10 and 11 quietly defied expectations. Launched in the early 1970s, these robotic explorers were supposed to coast through the cosmos with predictable precision, their paths governed by Newton's unshakable laws of motion. But by the 1980s, something peculiar emerged. Both probes were slowing down ever so slightly more than calculations predicted, as if an invisible hand were gently tugging them backward. This tiny discrepancy, barely a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, and for decades it haunted physicists like a ghost in the equations. At first, the anomaly seemed almost trivial, a rounding error perhaps, or an overlooked quirk in the spacecraft's design. But the more scientists scrutinized the data, the more stubbornly it refused to vanish. The Pioneer's deceleration was too consistent, too persistent to dismiss. If it wasn't a fluke, what could explain it? One leading theory pointed to heat. The probe's plutonium-powered generators emitted warmth, and even the faintest radiation pressure could, over years, nudge the spacecraft off course. It was like a car slowing down because someone left the heater on, subtle but measurable. Yet when researchers meticulously modeled every possible source of thermal recoil, the numbers still didn't quite add up. Then came the wilder ideas. Could the anomaly hint at a flaw in our understanding of gravity itself? Some theorists suggested modifications to Einstein's general relativity, proposing that gravity behaves differently at the solar system's edge. Others floated the existence of unseen matter, not dark matter, but something even more exotic, clinging to the outskirts of our cosmic neighborhood. For a while, the Pioneer Anomaly became a playground for fringe physics, a tantalizing crack where new theories could squeeze in. The mystery finally unraveled in 2012, when a team of researchers accounting for every last joule of heat radiating from the spacecraft's power systems found the missing piece. The Pioneer's own warmth, bouncing unevenly off their dish-shaped antennae, had been pushing them backward all along. The anomaly wasn't new physics, just an old-fashioned case of overlooked engineering. Yet its legacy endures. Those minuscule deviations forced scientists to question, to double-check, to leave no stone unturned. In the grand scheme of things, the Pioneer anomaly was a whisper, not a shout, but sometimes it's the quietest glitches that remind us how much we still have to learn. Because in the endless dark, even the smallest surprises can lead to the biggest revelations. In the constellation Cygnus, a star named KSE 8462852 behaves like no other. Nicknamed Tabby's star after astronomer Tabitha Boyajian, who first documented its bizarre flickering, this seemingly ordinary sun has confounded scientists with its erratic dimming, sometimes dropping in brightness by a staggering 22% before recovering, as if something colossal were passing in front of it. Unlike the predictable dips caused by orbiting planets, Tabby's star's light fluctuates chaotically with no discernible pattern. When the Kepler Space Telescope first spotted these anomalies, astronomers scrambled for explanations. Was it a swarm of comets, a fractured planet, or, as some daringly speculated, the signature of an alien megastructure? The most tantalizing early theory invoked a Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization to harness a star's power. The idea wasn't entirely far-fetched. After all, the star's light patterns didn't match any known natural phenomenon. But science demands evidence, and further observations tilted the scales toward less exotic, though no less puzzling, causes. Detailed analysis revealed that the dimming affected some wavelengths of light more than others, a telltale sign of dust, not solid megastructures. Yet this wasn't ordinary interstellar dust. It was fine, unevenly distributed, and constantly shifting, like a cosmic sandstorm with no clear origin. So where's all this dust coming from? One leading hypothesis points to a catastrophic collision in the star's asteroid belt, grinding rocky bodies into fine debris that now drifts in vast, irregular clouds. Another suggests a family of giant exocomets, their icy tails vaporizing as they plunge close to the star, leaving behind opaque veils of gas and dust. Both scenarios could explain the erratic dimming, but neither fully accounts for the star's long-term behavior. Over years of monitoring, Tabby's star has shown a gradual, overall decline in brightness, as if it's slowly being veiled by something far larger than passing comets or asteroids. The mystery deepens when you consider the star's history. Archival photographs from the 19th century reveal it was even brighter back then, dimming by nearly 14% over the past century. No known stellar process causes such a steady, prolonged fade, leaving astronomers to wonder, is Tabby's star eating its own planets? Could a series of planetary collisions have littered its orbit with debris, casting a growing shadow? Or is there an undiscovered stellar phenomenon at work, something beyond our current models of how stars age and interact with their surroundings? For now, Tabby's star remains an enigma, a cosmic oddball that refuses to fit neatly into any box. Projects like the Los Cumbres Observatory keep it under constant surveillance, alert for the next dramatic dimming event that might finally crack the case. Whether the answer lies in mundane astrophysics or something stranger, one thing's certain: this star has rewritten the playbook on how we interpret the cosmos. Every flicker, every dip, is a reminder that the universe still holds wonders we've yet to imagine, and sometimes the most ordinary-looking stars harbor the most extraordinary secrets. We think we know what the universe is made of: protons, neutrons, electrons. all the ordinary stuff that builds stars, planets, and even us. But here's the cosmic twist: about half of that normal matter, the Baryons physicists have tallied in their equations, has been missing for decades. You'd think finding half the universe's building blocks would be easy, but these elusive particles have been hiding in plain sight, woven into the fabric of space itself. The hunt for these missing baryons led scientists to an unexpected place: the vast, nearly invisible webs of hot gas stretching between galaxies. Picture the universe as a sponge, with galaxies clustered where the material is dense, and thin, scorching filaments of ionized gas threading the empty spaces. These filaments, heated to millions of degrees, glow faintly in X-rays, but they're so diffuse that for years our telescopes couldn't spot them. It's like trying to see a whisper in a hurricane. So why did it take so long to find them? Part of the challenge lies in their temperature. While hot enough to emit X-rays, these gas clouds are so spread out that their signal drowns in the cosmic noise. Even the most advanced X-ray observatories like Chandra and Newton struggled to pick them out. It wasn't until researchers turned to a clever workaround, studying how these filaments distort light from distant quasars, that the pieces started falling into place. By analyzing the subtle absorption lines in quasar spectra, astronomers could finally trace the fingerprints of this hidden matter. The discovery reshaped our understanding of the cosmic web. These baryons aren't lost, they're just camouflaged, woven into the universe's large-scale structure in a form we hadn't fully anticipated. Some theories suggest they were blown out of galaxies by supernova explosions or ejected by supermassive black holes, scattering across the voids like cosmic confetti. Others propose they've been there since the universe's infancy, part of the primordial soup that never fully condensed into galaxies. But the mystery isn't entirely solved. Even with these detections, there's still a gap between predictions and observations, leaving room for more surprises. Future missions like Athena, slated to launch in the 2030s, will peer deeper into these faint X-ray signals, hunting for the last traces of the universe's missing material. Every new observation brings us closer to a complete inventory of reality, because if we've overlooked something as fundamental as half the normal matter in existence, what else might we still be missing? The universe, it seems, is still full of accounting errors, and the ledger isn't closed yet. Zoom in far enough past atoms, past quarks, past anything we've ever seen, and the smooth fabric of spacetime might dissolve into chaos. At scales a billion trillion times smaller than an atom, where quantum mechanics and gravity collide, reality could be a seething ocean of virtual particles popping in and out of existence. This is quantum foam, the hypothetical froth at the foundation of everything, where the very notion of here and now breaks down into a turbulent dance of uncertainty. The idea traces back to physicist John Wheeler, who proposed that spacetime, when examined at the Planck length, might not be the serene continuum Einstein imagined. Instead, it could resemble a boiling pot of water, with bubbles of energy fluctuating so violently that the concepts of distance and duration lose all meaning. Imagine trying to measure the surface of a stormy sea with a ruler. Every time you place it down, the waves twist and distort your reading. Quantum foam could be doing the same to spacetime itself, making it fundamentally unmeasurable at the tiniest scales. But how do you detect something this elusive? Scientists are pushing technology to its limits. Some experiments hunt for faint distortions in light from distant gamma-ray bursts. If spacetime is grainy, high-energy photons traveling across the universe should scatter slightly, like light shimmering through frosted glass. Others look for subtle noise in gravitational wave detectors, searching for ripples that might betray the foam's turbulence. Even atomic clocks, the most precise timekeepers ever built, are being used to probe whether time itself stutters at microscopic scales. the implications are staggering. If spacetime is pixelated, black holes, already cosmic paradoxes, might churn this foam into a frenzy at their singularities, shredding the laws of physics entirely. The Big Bang, meanwhile, could have emerged from a quantum fluctuation in this primordial froth, a single bubble that inflated into our entire universe. Some theories even suggest that wormholes, those sci-fi staples, might be threaded through the foam's ever-changing structure, offering shortcuts across space-time, if only we could navigate them. Yet the foam remains theoretical, a ghost in the equations. Some models propose it's too fine-grained to ever detect, while others argue it might leave fingerprints in high-energy particle collisions. The debate isn't just academic, it's a battle over the nature of reality itself. Is the universe smooth and continuous, or is it built from invisible, churning pixels? The answer could redefine everything from gravity to the origin of existence. For now, quantum foam lingers at the edge of science, a tantalizing what-if that challenges our deepest assumptions. Every experiment that fails to find it only sharpens the mystery, forcing us to ask, are we not looking hard enough, or is the universe hiding its truest face behind a veil no tool can pierce? Until we know, the foam remains the ultimate cosmic tease, a reminder that even emptiness might be alive with secrets. Imagine sitting in a spaceship, engines roaring as you accelerate faster and faster through the void. Outside your window, the universe should look cold and empty, a perfect vacuum. But according to quantum physics, your motion could conjure heat from nothingness itself. This bizarre phenomenon is the Unruh effect, a quantum quirk where an accelerating observer detects a warm glow in what others would call empty space. It's as if the universe rewards movement with free energy, turning the vacuum into a cosmic mirage that shimmers with particles when you're pushing hard enough. The effect hinges on one of quantum field theory's strangest truths. The vacuum isn't truly empty. Even in complete darkness, particles flicker in and out of existence, their fleeting lives governed by Heisenberg's uncertainty principle. To an observer at rest, these virtual particles cancel each other out, leaving no trace, but accelerate, and the picture changes. Just as a speeding car splashes rain in its wake, acceleration disrupts the delicate balance of the quantum vacuum, transforming virtual particles into real, detectable heat. The faster you go, the hotter this phantom glow becomes, a thermal bath born purely from motion. Could this effect hold clues to some of cosmology's biggest puzzles? Some theorists speculate it might help explain dark energy, the mysterious force accelerating the universe's expansion. If empty space can radiate energy for accelerating observers, perhaps it also harbors a latent pressure driving galaxies apart. Others see parallels to Hawking radiation, the glow emitted by black holes. Both phenomena involve particles emerging from apparent nothingness, tied to the observer's perspective, hinting at a deeper link between acceleration, gravity, and quantum fields. Testing these ideas isn't easy. To feel the Unruh effect's warmth, you'd need to accelerate at 1 trillion times Earth's gravity, conditions only achievable near black holes or in hypothetical lab experiments with lasers. Yet researchers are pushing boundaries. Some propose using ultra-intense laser pulses to mimic extreme acceleration, while others look for subtle signatures in high-energy particle collisions. Even without direct proof, the Unruh effect reshapes how we think about reality. It suggests that particles aren't just out there, they're invitations, appearing only when we move through the universe in the right way. At its core, the Unruh effect blurs the line between observer and observed, reminding us that the cosmos isn't a static stage but an interactive performance. What we call reality might just be the universe's response to how we're moving through it, And if acceleration can conjure heat from the void, what else might be hiding in the quantum shadows, waiting for the right conditions to reveal itself? The answer could rewrite not just physics, but our place in the fabric of existence. That glowing ring of light piercing the cosmic darkness, the first ever image of a black hole's shadow, captured by the Event Horizon Telescope, didn't just make history. It tore open a new chapter in physics, centered in the haunting glow of galaxy M87. The supermassive beast known as M87 star revealed a fiery halo exactly as Einstein's equations predicted, warping spacetime so severely that even light couldn't escape its grip. But look closer and the details get weird. One side of that ring burns noticeably brighter, like a cosmic lopsided crown. Why? The answer isn't just about aesthetics, it's a clue to the black hole's spin, a fingerprint of its violent dance through the universe. This asymmetry comes from relativistic beaming, an effect straight out of Einstein's playbook. As superheated gas swirls around the black hole at near light speeds, the side spinning toward us appears brighter, its light amplified by the sheer force of its motion, while the receding side dims. It's like watching a cosmic carousel where the horses coming toward you shine headlights in your face, while those galloping away fade into the dark. But buried in that glow might be something even stranger: tiny flickers, echoes of light that could betray the quantum fabric of spacetime itself. Some theorists suggest these subtle fluctuations could be the smoking gun for quantum gravity, the long-sought theory to marry Einstein's relativity with the chaotic rules of the quantum world. If spacetime is granular at the tiniest scales, as quantum foam theories propose, the black hole's shadow might shimmer in ways no classical model can explain. Imagine throwing a pebble into a pond. The ripples should spread smoothly, but if the pond's surface were made of LIGO blocks, those ripples would stutter, jumping brick by brick. Similarly, if spacetime isn't perfectly smooth, the black hole's gravitational waves and light echoes might carry a faint, telltale jitter. The EHT team is already chasing these ghosts. By linking telescopes across the globe into a virtual instrument the size of Earth, they're refining M87 star's portrait to razor sharpness. Future upgrades could spot time delays in the ring's light, subtle delays where photons take slightly longer paths due to quantum fluctuations. Others are hunting for orbital echoes, patterns in the swirling plasma that might repeat like a skipped record, hinting at discrete quantum steps in spacetime's structure. Yet for all its precision, the image raises more questions than answers. Why does the ring's diameter match general relativity's predictions so perfectly, while the plasma around it moves in ways we can't fully model? Could the brightness variations encode secrets about the black hole's magnetic fields, or even the elusive no-hair theorem, which claims black holes are bald, devoid of any features except mass, spin, and charge? Every pixel in that image is a Rosetta Stone waiting for the right key to translate it. What's clear is this: M87 star isn't just a monster lurking in the void. It's a laboratory, a natural particle accelerator where gravity flexes its full might. And as the EHT sharpens its gaze, peeling back layers of that fiery ring, we're not just observing a black hole, we're decoding the universe's deepest rules written in light and shadow. The image was only the beginning. The real revelations are still coming into focus. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Born in the hearts of stars, supernova, and even nuclear reactors, these nearly massless phantoms rarely interact with matter, making them fiendishly hard to detect. But here's the twist: when scientists finally catch them, they don't always behave the way they should. The standard model of particle physics tells us neutrinos should come in three flavors: electron, muon, and tau, and oscillate between them as they travel. Yet experiments keep picking up strange discrepancies, as if these particles are playing by rules we haven't discovered yet. One of the most puzzling anomalies comes from the LSD and mini-Baryons experiments, which detected more neutrino oscillations than the three-flavor model predicts. It's like setting up a game of cosmic hide and seek where you expect three players, but the shadows keep moving as if there's a fourth hiding in plain sight. This mismatch has led to a radical idea. What if a fourth type of neutrino exists, one so stealthy it doesn't even interact with the weak nuclear force? Dubbed the sterile neutrino, this hypothetical particle would be the ultimate cosmic lurker, detectable only through its gravitational pull and its subtle meddling with other neutrinos' behavior. The implications are staggering. If sterile neutrinos are real, they could be the key to some of the universe's biggest mysteries. Dark matter, for instance, that invisible glue holding galaxies together, might be made of these ghostly particles. Some theories even suggest sterile neutrinos could explain why the universe has far more matter than antimatter, solving a cosmic imbalance that's puzzled physicists for decades. But proving their existence is another challenge entirely. Unlike their ordinary cousins, sterile neutrinos wouldn't leave a trace in particle detectors, forcing scientists to hunt for them indirectly through their influence on the oscillations of other neutrinos. Not everyone's convinced, though. Alternative explanations range from flaws in experimental setups to undiscovered quirks in how neutrinos interact with matter. The reactor antineutrino anomaly, for example, shows a consistent deficit in detected neutrinos from nuclear reactors, another mismatch that could point to sterile neutrinos or simply gaps in our understanding of reactor physics. Meanwhile, experiments like IceCube and Fermilab's short baseline neutrino program are racing to either confirm or debunk the anomaly, placing detectors deep underground or firing neutrino beams through hundreds of miles of rock to catch these phantoms mid-oscillation. The stakes couldn't be higher. If sterile neutrinos exist, they'd be the first major addition to the standard model in decades, forcing a rewrite of particle physics' most sacred rulebook. If they don't, then the anomalies must stem from something equally profound, perhaps new forces, hidden dimensions, or even flaws in quantum theory itself. Every flicker in the data, every unexpected detection, is a whisper from the universe, hinting at a reality far stranger than we've imagined. And as detectors grow more sensitive and experiments more precise, one thing's certain: the neutrinos' secrets won't stay hidden forever. They're out there, slipping through our fingers and through everything else waiting to be caught. At the heart of our galaxy, where stars crowd so tightly they form a glowing snowstorm in telescope images, there's a mystery brewing, an eerie excess of gamma rays, the universe's most energetic light. The Milky Way's core should shine predictably, its glow driven by known sources like pulsars and cosmic rays colliding with gas. But when scientists analyzed data from the Fermi Gamma Ray Space Telescope, they found something unexpected: a diffuse, relentless gamma ray haze that shouldn't be there. It's as if the galactic center is hiding a cosmic bonfire, radiating energy with no clear source. One tantalizing explanation points to dark matter, the universe's most elusive substance. According to some theories, when dark matter particles collide, they could annihilate each other in bursts of gamma rays. The galactic center, packed with dark matter's gravitational pull, would be the perfect place for this phantom fireworks show. The excess's smooth, symmetrical spread matches predictions for such annihilations, as if we're glimpsing the invisible scaffolding of the universe finally revealing itself through flashes of light. But not everyone's convinced. Skeptics argue the glow could come from a dense population of pulsars, the rapidly spinning corpses of dead stars, which beam gamma rays like cosmic lighthouses. These objects are faint individually, but en masse they might mimic a smooth excess. The debate hinges on a cosmic game of hide and seek. Are we seeing thousands of undiscovered point sources, or a true diffuse signal? Advanced algorithms have scoured Fermi's data, teasing apart the gamma-ray fog, but the results remain frustratingly ambiguous. Some studies claim to spot faint pulsar-like flickers within the excess, while others insist the glow is too uniform to stem from discrete objects. Then there's the wild card. Could something entirely different be at play? The galactic center is a chaotic place, home to a supermassive black hole, swirling gas clouds, and magnetic fields strong enough to twist spacetime. Unknown astrophysical processes, perhaps particle acceleration in turbulent plasma, or interactions with dark matter's more exotic cousins, might be lighting up the gamma-ray sky in ways we haven't yet imagined. The stakes are high. If the excess is dark matter's calling card, it would be the first direct clue to its nature, a breakthrough decades in the making. If it's pulsars, it would force us to rethink how these stellar remnants form and cluster. And if it's neither, well, that's when things get really interesting. Future telescopes, like the Cherenkov Telescope Array, aim to dissect the excess with sharper precision, hunting for spectral fingerprints that could settle the debate. Until then, the galactic center's ghostly glow remains a cosmic Rorschach test, one that keeps astronomers awake at night, staring at the data, wondering what secrets the universe is still hiding in plain sight. When gravitational waves ripple through the cosmos, warping spacetime itself, they often arrive with a cosmic fanfare, flashes of light, bursts of gamma rays, or even glowing kilonova explosions. But sometimes these ripples slip through the universe in eerie silence, leaving astronomers staring at empty patches of sky, wondering where the light went. LIGO, the Laser Interferometer Gravitational Wave Observatory, has detected dozens of these space-time tremors since its first groundbreaking discovery in 2015. Yet the more signals it captures, the clearer it becomes. Not all collisions play by the same rules. Take neutron-star mergers, for example. When two of these ultra-dense stellar corpses spiral together, they're supposed to unleash a fireworks show, gamma-ray bursts, X-rays, and a radioactive glow called a kilonova, forged from the gold and platinum they scatter into space. That's exactly what happened in 2017, when LIGO spotted GW 170817, a neutron star collision that lit up telescopes across the electromagnetic spectrum. But then there was GW 190425, a gravitational wave that matched the profile of a neutron-star merger but left the skies dark. No flash, no glow, no trace. It was as if the stars had vanished into the void, leaving only a gravitational echo behind. Black holes, on the other hand, are notorious for their stealth. With no surface to crash into and no material to ignite, their mergers were long assumed to be invisible. Yet even here, nature finds ways to surprise. In 2020, astronomers reported a flicker of light coinciding with a black hole merger, a flare that shouldn't exist unless the black holes were swimming in a dense disk of gas, or perhaps dragging stars along with them. Then there's the puzzle of mismatched masses. Some black hole pairs are nearly identical in size, while others are wildly uneven, like a bowling ball merging with a marble. These lopsided collisions might warp spacetime differently, potentially leaving faint electromagnetic breadcrumbs we don't yet know how to spot. So why the inconsistency? One possibility is that some neutron stars collapse into black holes the instant they collide, swallowing any light before it can escape. Others might form hypermassive neutron stars first, lingering just long enough to blast out radiation before vanishing. Environment matters too. A merger buried deep in a star-forming nebula might hide its light behind curtains of dust, while one in the emptiness of intergalactic space would shine unobstructed. And then there's the wild card. What if some of these events aren't neutron stars or black holes at all, but something more exotic, like quark stars or primordial black holes, entities that defy our current playbook entirely? The anomalies aren't just gaps in our knowledge, they're windows into the unknown. Every silent gravitational wave, every unexpected flash, forces us to rethink the extremes of physics. With upgrades to LIGO and new detectors like the Einstein telescope on the horizon, we're on the verge of catching even fainter ripples, probing deeper into the chaos of cosmic collisions. The universe, it seems, has a flair for the dramatic, and the next signal could be the one that rewrites the rules entirely. Among the countless dying stars in our galaxy, the Red Rectangle Nebula stands out like a cosmic abstract painting, a geometric enigma glowing with spectral secrets. Named for its striking, almost perfectly rectangular shape when viewed from Earth, this celestial oddity isn't just visually arresting. Its light carries chemical fingerprints that have left scientists baffled. When astronomers analyze its spectrum, they find sharp, unexplained spikes unlike the usual smooth curves of stellar emissions. These jagged lines suggest something extraordinary: complex organic molecules, possibly polycyclic aromatic hydrocarbons, floating in the nebula's dusty expanse. On Earth, these very same molecules are found in coal, soot, and even the building blocks of life. Could the Red Rectangle be a cosmic factory for the ingredients of biology, or is it simply an exotic chemical anomaly? The nebula's symmetry only deepens the mystery. Most planetary nebulae, the glowing shells of gas ejected by dying stars, are chaotic, bubble-like structures. But the Red Rectangle's near-perfect right angles defy expectations, shaped by two cones of gas ejected in opposite directions from a central binary star system. As these cones intersect, they create the illusion of a geometric masterpiece, a structure so precise it seems almost artificial. Some theorists speculate that dense dust disks around the stars act like cosmic stencils, sculpting the outflowing gas into this rare form. Yet even this explanation doesn't fully account for the nebula's crisp edges or the peculiar distribution of its mysterious molecules. Then there's the question of origins. The organic compounds detected here aren't just floating freely. They're thriving in an environment bathed in intense ultraviolet radiation, a place where such fragile molecules should be ripped apart. How are they surviving? One possibility is that they're shielded within tiny dust grains, like treasures locked in interstellar safes. Alternatively, they might be constantly reforming, with chemical reactions in the nebula's turbulent gas churning out new organic material as fast as the radiation destroys it. If true, the Red Rectangle could be a blueprint for how complex chemistry persists, or even flourishes in the harshest corners of the universe. The implications ripple far beyond this one nebula. If organic molecules can form and endure in such extreme conditions, they might be far more common in space than we ever imagined. That raises a tantalizing prospect. Could the raw materials for life be scattered across the cosmos, seeded by dying stars like this one? Or is the Red Rectangle a rare fluke, its chemistry as unique as its shape? Future telescopes like the James Webb Space Telescope aim to dissect its light with even greater precision, hunting for clues in the nebula's molecular fingerprints. Every new observation peels back another layer, revealing not just the secrets of a single star's death, but potentially the birth of something much greater, a cosmic recipe written in light and dust, waiting to be decoded. If advanced civilizations exist, why haven't they built Dyson spheres? these hypothetical megastructures, enormous shells or swarms of energy collectors designed to harness a star's full power, should be glaringly obvious in our telescopes. A single Dyson sphere would blot out its star's visible light, radiating only waste heat in infrared wavelengths. Yet despite decades of searching, we've found no definitive signs of these cosmic power plants. The silence isn't just puzzling, it's forcing us to confront a chilling possibility. Either interstellar engineering is far harder than we've imagined, or civilizations capable of such feats don't last long enough to build them. The search for Dyson spheres hasn't been idle speculation. Astronomers have scoured infrared surveys for unusual heat signatures, targeting stars that emit too little visible light and too much infrared, exactly what a partially completed Dyson swarm might look like. A few candidates have emerged, like KIC 8462852, better known as Tabby star, with its erratic dimming patterns, but none have met the strict criteria for a confirmed megastructure. The most promising leads often crumble under scrutiny, revealing natural explanations like dust clouds or interstellar debris. It's as if the universe is taunting us with near misses, dangling possibilities just out of reach. So where is everybody? One unsettling answer is that Dyson spheres might be deliberately hidden. A civilization advanced enough to dismantle planets for construction materials could also cloak its activities, redirecting waste heat into undetectable wavelengths or using stellar engineering to mimic natural phenomena. Imagine an ant colony searching for humans but only looking for campfires, missing cities, power grids, and satellites entirely. Our search methods might be too primitive to recognize a type Roman II civilization's true footprint. Then there's the darker alternative. Perhaps no civilization survives long enough to reach that scale. The leap from planetary to stellar engineering might require millennia of stability, no wars, no resource collapses, no self-inflicted catastrophes. The Great Filter, a hypothetical barrier preventing life from advancing to interstellar scales, could loom just ahead of us, waiting to snuff out any species that comes too close. Every silent star becomes a warning, a cosmic gravestone for civilizations that burn too bright and too fast. Yet the search continues, driven by stubborn optimism. New telescopes like the James Webb Space Telescope and the upcoming Vera Rubin Observatory could spot subtler signatures, perhaps partial Dyson swarms or transient megastructures under construction. Others propose looking for gravitational lensing effects or unusual laser emissions, signs of a civilization not just harnessing starlight but manipulating spacetime itself. The Dyson dilemma cuts to the heart of the Fermi Paradox. It's not just about finding aliens, it's about confronting the limits of technology, the fragility of civilizations, and the haunting question of whether the stars are forever out of reach. Every silent sky isn't just an absence of evidence. It's a mirror reflecting back our own precarious place in the universe. Black holes have long been the universe's ultimate one-way streets, cosmic traps where matter vanishes, never to return. But what if the equations hiding in Einstein's theory of relativity hold a secret backdoor? Enter white holes, the theoretical opposite of black holes. Where a black hole's gravity is so strong nothing escapes, a white hole would violently repel anything approaching it, spewing out matter and energy like a cosmic fire hose. The math allows it. Flip a black hole's equations in time and you get a white hole, a region of space-time where nothing can enter but everything must exit. It's as if the universe has a rewind button for singularities, turning collapse into explosion. The catch, no one's ever seen one. White holes remain purely hypothetical, lurking in the realm of pencil and paper physics. Yet their potential implications are staggering. Some theorists suggest white holes could be the aftermath of a black hole's life cycle. When a black hole evaporates via Hawking radiation, might it rebound as a white hole in its final moments, transforming from an insatiable devourer into a radiant fountain? Others propose even wilder ideas. Could the Big Bang itself have been a white hole event, a singularity erupting into our universe from some other dimension or timeline? Then there's the quantum connection. In loop quantum gravity, a leading theory attempting to unify relativity and quantum mechanics, black holes might naturally transition into white holes over immense timescales. Instead of collapsing into an infinitely dense point, a black hole's core could hit a quantum bounce, reversing its collapse into an explosion. If true, every black hole in the universe could one day become a white hole, recycling spacetime itself. But why the silence? If white holes exist, why don't telescopes catch these cosmic geysers in action? One possibility is that they're incredibly short-lived, flaring into existence and vanishing before we can spot them. Another is that they're disguised. What we perceive as gamma-ray bursts or other high-energy phenomena might actually be white holes in disguise, or perhaps they're hiding in plain sight, their emissions blending into the background hum of the universe. The search isn't hopeless. Some astronomers scan for unexplained high-energy outbursts that lack the usual signatures of supernova or neutron star collisions. Others model how a white hole's light would be distorted by its own extreme gravity, hunting for telltale spectral fingerprints. The challenge is separating a true white hole signal from the universe's countless other fireworks. Whether real or just a mathematical curiosity, white holes force us to rethink the boundaries of physics. They blur the line between beginning and end, suggesting that even the most voracious monsters in space might have a second act. And if they're out there lurking in the data or waiting to erupt, they could rewrite not just the story of black holes, but the origin of everything. The universe, it seems, loves symmetry. And for every door that closes, there might just be another somewhere bursting open. Galaxies are supposed to follow rules, dark matter's gravitational glue holding their stars together, keeping them from flying apart as they spin. But in 2018, astronomers stumbled upon a cosmic rule breaker, NGC 1052DF2, a galaxy that seems to play the game without the universe's most essential player. This ghostly patch of stars, floating 65 million light-years away, weighs in shockingly light. Its visible matter accounts for nearly all its mass, leaving almost no room for dark matter's invisible grip. It's like finding a car speeding down the highway with no engine. How does it even move? The discovery sent shockwaves through astrophysics. Dark matter isn't just a minor ingredient, it's the cosmic scaffolding that shapes how galaxies form and behave. Take the Milky Way. Without dark matter's gravitational anchor, our galaxy's outer stars would orbit far slower than they do. Yet NGC 1052DF2 stars move at precisely the speeds predicted by its visible mass alone, as if dark matter never showed up to the party. Some researchers initially dismissed it as a fluke, a cosmic oddity where dark matter somehow got stripped away. But then came NGC 1052DF4, another galaxy in the same neighborhood with the same puzzling deficit. Suddenly, the exceptions were adding up. So where did the dark matter go? One theory suggests a violent past, perhaps a close encounter with a massive galaxy, ripped away its dark matter like a thief in the night. Computer simulations show such thefts are possible, with tidal forces peeling dark matter from a smaller galaxy while leaving its stars relatively untouched. The problem, NGC 1052DF2, shows no signs of trauma, no twisted arms or stellar streams betraying a recent collision. It's eerily pristine, floating in isolation like it was born this way. Then there's the radical alternative. What if dark matter isn't as universal as we thought? most galaxies conform to dark matter's rules because, under normal conditions, visible matter collapses inside dark matter halos during formation. But perhaps NGC 1052DF2 assembled differently, its stars coalescing in a rare region where dark matter was scarce from the start. If true, it would mean galaxies can form through multiple pathways, some with dark matter's help, others without. The debate isn't just academic. If galaxies can exist without dark matter, it challenges the very foundation of modern cosmology. Maybe dark matter isn't a particle at all, but a sign that gravity behaves differently on cosmic scales. Modified Newtonian dynamics, or MUND, proposes tweaking gravity's laws to explain galactic motions without invoking invisible matter. Yet MUND struggles to explain phenomena like the bullet cluster, where dark matter's gravitational shadow is unmistakable. NGC 1052DF2 doesn't fit neatly into either camp, leaving scientists scrambling for new models. For now, this galactic rebel remains an enigma, a reminder that the universe delights in throwing curveballs. Whether it's a cosmic accident or a clue to deeper physics, one thing's certain: the rulebook isn't finished. Every outlier like NGC 1052DF2 forces us to ask whether we've misunderstood the game entirely. And in those questions, hidden between the lines of data and theory, might just be the next great leap in understanding the cosmos. The Planck satellite was supposed to map the cosmic microwave background with such precision that it would confirm our universe's origin story, a smooth, uniform expansion from the Big Bang. Instead, its data revealed unsettling wrinkles in spacetime's baby pictures. One of the most glaring anomalies, the CMB isn't perfectly symmetrical. The northern hemisphere of the observable universe appears slightly cooler than the southern, as if the Big Bang's afterglow was lopsided from the very beginning. This cosmic asymmetry, nicknamed the axis of evil, defies the cosmological principle, the bedrock assumption that the universe should look the same in all directions. It's like baking a cake and finding one side inexplicably denser than the other, despite mixing the batter evenly. But the quirks don't stop there. Planck's measurements also uncovered strange, unexplained cold spots and anomalous dips in the CMB's power spectrum, places where the universe's primordial vibrations seem muted, as if something was absorbing energy before light could travel freely. These aren't minor statistical blips. The odds of such patterns arising by chance are less than 1 in 1,000, forcing scientists to confront a radical possibility. Could these be scars from a time before the Big Bang? Enter brain cosmology, a mind-bending framework where our universe isn't the only one. Imagine reality as a stack of floating membranes, higher dimensional brains drifting through an even grander space. If two of these brains collided, the energy of their impact could have sparked our Big Bang, leaving behind asymmetries in the CMB like fingerprints on glass. The cold spots, perhaps bruises from where the brains grazed each other unevenly. The lopsided temperature map, a cosmic tilt inherited from the angle of collision. Not everyone's convinced, of course. Skeptics argue the anomalies might stem from mundane sources, galactic dust distorting measurements, or residual noise in Planck's instruments. Yet, even after accounting for these factors, the signals persist. Others propose less exotic fixes, like tweaking inflation theory to allow for uneven expansion in the universe's first moments. But the brain hypothesis lingers because it offers something unique, a testable narrative. If our universe was born from a collision, gravitational waves from that event might still ripple through the cosmos, imprinting a telltale swirl pattern on the CMB's polarization. Future telescopes hunting for these swirls could finally settle the debate. The implications are staggering. If Planck's anomalies are indeed echoes of a pre-Big Bang reality, then time, space, and causality, as we know them, might just be local phenomena, a single chapter in a much larger multiverse saga. It's a humbling thought. The universe's birth certificate might not be its first page after all, and somewhere in those asymmetries, those cold spots, could lie clues to a past we've barely begun to imagine. Most stars don't survive a supernova. They either collapse into black holes, shrink into neutron stars, or scatter their remains across the cosmos in a blaze of glory. But LP 4365 is different. This rogue star, hurtling through the Milky Way at nearly 2 million miles per hour, is something far stranger. A cosmic zombie, the charred remnant of a white dwarf that somehow endured its own violent explosion. Unlike the usual stellar corpses, LP 4365 didn't just die, it partially exploded, lost most of its mass and kept on going, a runaway fragment of what was once a star. What makes these supernova survivors so baffling is their composition. Most white dwarfs are dense spheres of carbon and oxygen, the spent fuel of stars like our Sun. But LP 4365 is laced with neon, oxygen, and heavy metals, elements forged in the extreme heat of a supernova's blast wave. It's as if the star's outer layers were violently stripped away, leaving behind a mangled core that somehow escaped total destruction. The key might lie in the explosion's asymmetry. Most models assume supernova detonate uniformly, but if a white dwarf's explosion was lopsided like a firework with a faulty fuse, it could have kicked the surviving fragment clear of the blast zone, sending it careening through space like a cosmic shrapnel. These zombie stars aren't just stellar oddities, they're time capsules. Their trajectories trace back to ancient supernova, offering clues about how these explosions unfold. By studying LP 4365's speed and trajectory, astronomers have reconstructed its violent past. Roughly 5 million years ago, it was part of a binary system, siphoning material from its companion until it grew unstable and detonated. The explosion should have annihilated both stars, yet here it is, a phantom, still glowing with the aftermath of its near-death experience. Even stranger, LP 4365 isn't alone. Stars like SDSS J124+111 and D6 are also racing through the galaxy, bearing the same scars of partial destruction. Their existence suggests that asymmetric supernova might be more common than we thought, challenging textbook models of stellar death. If stars can cheat death like this, what else have we gotten wrong about the life cycles of the cosmos? The answer might lie in the next generation of telescopes, which could uncover more of these stellar survivors, each one a testament to the universe's capacity for rebellion, even against its own laws. For now, LP 4365 continues its lonely journey, a celestial ghost story written in light and motion. It's a reminder that in the chaos of the cosmos, even destruction isn't always final. Sometimes, against all odds, a star refuses to fade quietly, and in its defiance, it illuminates the darkest corners of astrophysics. Moons have always been more than just companions to planets. They're worlds in their own right, with landscapes as diverse as the imagination. But what about moons beyond our solar system? The hunt for Exomoons, natural satellites orbiting distant exoplanets, has become one of astronomy's most tantalizing quests. Take Kepler 1625b, the first serious Exomoon candidate. This potential moon, possibly the size of Neptune, orbits a gas giant 8,000 light-years away. If confirmed, it would shatter every notion we have about lunar formation. A moon that massive shouldn't exist under current models, yet there it is, lurking in the data, defying expectations. Detecting Exomoons is like trying to spot a firefly hovering next to a lighthouse while standing miles away. The techniques astronomers use are ingenious, pushing telescopes and algorithms to their absolute limits. When an exoplanet transits its star, causing a dip in brightness, researchers scour the light curve for secondary dips, tiny blips that might betray an orbiting moon's presence. Sometimes they look for gravitational tugs, where a moon's pull makes the planet wobble slightly, altering the timing of its transits. Even then, the signals are whisper-thin, buried in noise. Kepler 1625b's discovery hinged on 3 painstakingly observed transits, each with a peculiar light pattern that didn't quite fit a planet alone. The data suggested something else was there, something massive, something unseen. But the real enigma isn't just finding these moons, it's figuring out how they could exist. A Neptune-sized moon shouldn't form in place around a gas giant. It's too big. One theory suggests it might be a captured planet, snatched by its host's gravity in a celestial tug-of-war. Another posits a cataclysmic collision, where debris coalesced into an oversized lunar companion. Whatever the origin, its existence would force us to rewrite the rules of moon formation, proving the cosmos is far more creative than we've given it credit for. Then there's the ultimate question: could exomoons harbor life? Gas giants in habitable zones often host multiple moons, and with tidal heating, the same force that keeps Jupiter's Europa and Saturn's Enceladus geologically active, a moon like Kepler 1625b might have subsurface oceans shielded from harsh stellar radiation by its planet's magnetic field. Imagine an entire ecosystem thriving beneath the ice of a moon we've never even seen directly, its existence inferred from flickers of light. The search is far from over. New observatories like the James Webb Space Telescope and the upcoming European Extremely Large Telescope will bring sharper eyes to the hunt, probing exoplanetary systems for lunar shadows and gravitational quirks. Every candidate, every flicker in the data, could be the key to unlocking a new class of worlds, places where the night sky isn't dominated by a sun, but by the swirling face of a giant planet casting its glow over alien landscapes. The universe has already shown us it's full of surprises. Exomoons might just be the next great revelation, waiting in the shadows of distant stars. Quantum entanglement is strange enough on its own, particles linked across vast distances, instantly mirroring each other's states no matter how far apart they are. But throw black holes into the mix and the phenomenon becomes downright surreal. In 2013, physicists Leonard Susskind and Juan Maldacena proposed a radical idea. What if entanglement isn't just a quantum quirk but a physical connection, a microscopic wormhole stitching particles together through the fabric of spacetime? They called it ER equals EPR, a mashup of 2 landmark theories. ER refers to Einstein and Rosen's wormholes, hypothetical tunnels through spacetime. EPR stands for Einstein, Podolsky, and Rosen's famous paradox about entangled particles. The equation suggests these aren't separate ideas at all, they're 2 sides of the same cosmic coin. At first glance, the math checks out. Just as entangled particles share a hidden bond, wormholes create shortcuts between distant points. But the real magic lies in the implications. If ER equals EPR holds, it could bridge quantum mechanics and general relativity, the 2 pillars of modern physics that have stubbornly refused to reconcile. Quantum theory governs the tiny world of particles, while Einstein's relativity shapes the vast cosmos. Black holes, where both realms collide, might be the key to unlocking a theory of everything. Imagine spacetime as a tangled web of these microscopic wormholes, their threads weaving the universe into a seamless whole. Every entangled pair, from lab experiments to particles born in the early universe, could be invisibly tethered by spacetime itself. Testing this idea isn't for the faint of heart. How do you detect a wormhole too small to see, let alone traverse? One approach involves black hole analogs tabletop experiments using ultra-cold atoms or lasers to simulate the mind-bending physics of entanglement and horizons. Another strategy leans on quantum computers, programmed to model how information might traverse these hypothetical bridges. Already, researchers have found tantalizing hints. Certain entangled systems behave mathematically like wormholes, with correlations mirroring the flow of information through a tunnel. In 2022, a groundbreaking experiment used a quantum processor to simulate a holographic wormhole, observing signals that echoed the predictions of ER equals EPR. It wasn't a real wormhole, of course, but a shadow play of the underlying physics, a glimpse into how spacetime might encode its deepest secrets. Yet the mystery deepens when you consider black holes. According to quantum mechanics, information can't be destroyed, but black holes seem to obliterate it when they evaporate. ER equals EPR offers a way out. If particles inside and outside a black hole are entangled via wormholes, the information might not vanish. It could be scrambled and preserved in the spacetime fabric itself. This could solve the infamous black hole information paradox, while painting a universe where entanglement isn't just a feature but the architecture of reality. The implications ripple beyond theory. If wormholes and entanglement are truly linked, could we one day harness them? The idea of stable, traversable wormholes remains speculative, but the math suggests that under extreme quantum conditions like negative energy or exotic matter, these bridges might stabilize. For now, ER equals EPR remains a dazzling hypothesis, a thread connecting the smallest particles to the cosmos's grandest structures. But with every experiment, every simulation, we're tugging at that thread, unraveling a universe far more connected than we ever dreamed. Dark energy is the universe's silent puppeteer, an unseen force stretching the cosmos apart at an accelerating pace. But what if its grip isn't just relentless? What if it's growing stronger? This is the chilling premise of the phantom energy catastrophe, a scenario where dark energy doesn't just push galaxies apart, but escalates its assault until spacetime itself unravels. Unlike the Big Crunch, where gravity pulls everything back into a singularity, or the heat death, where the universe fades into cold stillness, the Big Rip is a cosmic apocalypse of pure disintegration. Picture a universe where dark energy's pressure intensifies exponentially, first flinging galaxies beyond the visible horizon, then tearing stars from their orbits, and finally, in its final, violent act, splitting atoms into quarks and scattering them into the void. It's not just the end of matter, it's the end of physics as we know it. The key to this nightmare lies in dark energy's equation of state, a measure of how its density changes over time. If dark energy behaves like Einstein's cosmological constant, unchanging and uniform, the universe faces a slower, more dignified expansion. But if it's phantom energy, a hypothetical form with negative pressure that grows stronger as space expands, the equation flips. The more the universe stretches, the more phantom energy pours into the vacuum, creating a feedback loop of self-destruction. Some models suggest this could happen in as little as 20 billion years, a blink in cosmic time, rendering the universe unrecognizable long before stars like our sun finish burning out. Yet not all hope is lost. Observations of distant supernova and galaxy clusters hint that dark energy's strength might indeed vary, but whether it's phantom or something tamer remains hotly debated. The Dark Energy Survey and upcoming Euclid mission are mapping the universe's expansion with unprecedented precision, hunting for clues in the subtle warping of light around massive structures. If phantom energy is real, its fingerprints should appear in these distortions, subtly altering how galaxies cluster over time. There's a wild card, though: quantum gravity. At the precipice of the Big Rip, space-time would stretch so thin that quantum effects might dominate, potentially triggering a phase transition, a cosmic reset button. Some theories suggest a new universe could bubble into existence from the wreckage, inheriting nothing of our physics but offering a bizarre form of cosmic redemption. Others propose that dark energy's evolution could stabilize, as yet undiscovered fields interact to balance its influence. The phantom energy scenario forces us to confront a humbling truth: the universe's fate isn't written in stone. It's a dynamic equation with dark energy as the ultimate variable. Whether it's a slow fade, a fiery collapse, or a violent shredding, the answer lies in the dark, waiting to be uncovered by the next generation of telescopes, the next breakthrough in theory, or perhaps by the universe itself, as it whispers its secrets across the expanding void. What if everything around us, the stars, the laws of physics, even your thoughts, isn't fundamentally real, but an unfathomably complex simulation running on some advanced civilization's quantum computer? This isn't science fiction, it's the simulation hypothesis, a serious argument debated by physicists and philosophers alike. The idea hinges on a simple but staggering premise: if a civilization could create simulations indistinguishable from reality, and if they had the motivation to do so, the statistical odds suggest we're far more likely to be living in one of those simulations than in the base reality. Think of it like this: if you had a video game with NPCs so advanced they believed they were conscious, how would they ever prove they weren't just lines of code? The argument gained traction when Oxford philosopher Nick Bostrom formalized it in 2003, outlining a trilemma. Either civilizations never reach the technological capacity to simulate universes, they choose not to, or we're almost certainly inside a simulation ourselves. But what pushes this thought experiment into the realm of scientific inquiry are the peculiar quirks of quantum mechanics, the very rules that govern reality at its smallest scales. Take the double-slit experiment, where particles behave as waves or particles depending on whether they're observed. Some theorists argue this observer effect resembles a video game's rendering engine. Details only resolve when measured, saving computational power. Even more provocative are claims like those of Silicon Valley mogul Elon Musk, who famously stated the odds we're in base reality are 1 in billions. Yet critics push back hard. They point out that the universe's sheer complexity, down to every quantum fluctuation in every atom, would require processing power beyond anything imaginable, even for an ultra-advanced civilization. Others argue the hypothesis isn't falsifiable. If the simulation is flawless, no test could ever expose it, making the idea more metaphysics than physics. But intriguingly, some scientists are actively hunting for glitches. One approach examines high-energy cosmic rays. If spacetime is pixelated at the tiniest scale, a hallmark of a simulated reality, these rays should interact with the universe's underlying resolution limit, subtly breaking Einstein's relativity at extreme energies. So far, no such anomalies have been found. The simulation hypothesis forces us to confront existential questions that blur science and philosophy. If we're in a simulation, who programmed it? Are there nested layers of simulations within simulations? And most unsettling of all, if we one day create our own hyper-realistic simulations, would that make us gods or prisoners in someone else's code? The debate may never have a definitive answer, but it reveals something profound about our place in the cosmos. Reality, whatever its nature, is far stranger than we've dared to imagine. Picture our universe not as a solitary island floating in darkness, but as one bubble in an endless cosmic foam, a single soap suds in an ocean of froth. This is the multiverse hypothesis in its most vivid form, where countless bubble universes, each with their own unique laws of physics, may be inflating and colliding beyond the edges of our observable reality. The idea stems from eternal inflation theory, which suggests that the rapid expansion of spacetime during the Big Bang never truly stopped. Instead, it continues in distant regions, birthing new universes like bubbles in a boiling pot, each one a self-contained reality where gravity might be stronger, light slower, or the very atoms we're made of impossible. The mind-bending question is, if these bubbles exist, could we ever detect them? The answer might lie in the oldest light we can see, the cosmic microwave background. When two bubble universes brush against each other, the collision could send shockwaves rippling through space-time, leaving behind telltale imprints in the CMB's temperature patterns. Imagine pressing two soap bubbles together. The boundary where they meet forms a faint, circular wrinkle. Cosmologists hunt for similar bruises in the microwave sky, anomalous rings of temperature fluctuations that defy conventional explanations. Some researchers claim to have spotted these signatures already, like the infamous cold spot, a vast, unexplained chill in the CMB that could be the scar of an ancient cosmic collision. But proving these marks come from another universe is no easy feat. Alternative explanations abound. Perhaps they're statistical flukes, remnants of primordial black holes, or distortions from interstellar dust. The challenge is separating the signal from the noise in a universe that's already brimming with mysteries. Future telescopes, like the Simons Observatory and CMB S4, aim to map the CMB with unprecedented precision, scanning for patterns that match theoretical predictions of bubble collisions. If they find a match, it would be the first tangible evidence that our universe isn't alone, just one page in an infinite cosmic library. Yet even if we never detect these bruises, the multiverse idea reshapes how we think about reality. It suggests that the constants we take for granted, the speed of light, the strength of gravity, might not be fundamental truths but local bylaws, quirks of our particular bubble. In another universe, stars might burn with different fuels or not form at all. Some bubbles could collapse instantly, others might teem with life we can't even imagine. The multiverse isn't just a theory, it's a mirror, forcing us to confront whether our universe's order is inevitable or a single roll of the dice in a game without end. The hunt for these cosmic fingerprints isn't just about physics, it's about philosophy. If bubble universes are real, they redefine our place in existence, turning the cosmos from a solitary stage into a bustling metropolis of realities, each humming with its own strange tune. And somewhere in the static of the CMB, in those faint, elusive rings, might lie the answer to the ultimate question: are we alone, or just one voice in a choir too vast to comprehend? Time crystals sound like something straight out of science fiction structures that repeat not in space, like diamonds or snowflakes, but in time, ticking through patterns that never settle into equilibrium. Imagine a clock that winds itself forever without batteries, or a snowflake that melts and reforms in an endless loop without any energy input. This bizarre state of matter was once thought impossible, a direct violation of thermodynamics' sacred rule that all systems must eventually reach balance. Yet in 2016, researchers created the first time crystals in the lab, using chains of ytterbium ions doused with laser pulses. The result: a quantum system that cycles between two distinct configurations indefinitely, like a pendulum swinging back and forth without friction, never winding down. How do they cheat the universe's relentless push toward disorder? The secret lies in a loophole called many-body localization. Normally, energy spreads evenly through a system until it reaches equilibrium. That's why your coffee cools and pendulums stop. But time crystals exploit quantum weirdness to trap energy in a repeating dance, preventing it from dissipating. It's like a crowd doing the wave in a stadium. Even if no new energy is added, the pattern keeps circulating because the participants here, entangled quantum particles, are locked in sync. This isn't perpetual motion. It's a new phase of matter, one that flips our understanding of stability on its head. The implications are staggering. Time crystals could revolutionize quantum computing by creating ultra-stable qubits resistant to decoherence, the bane of quantum systems that crumble at the slightest disturbance. Picture a quantum processor where information isn't stored in fragile states but in indestructible rhythms, immune to noise. Others speculate these crystals might unlock exotic physics, like time quasi-particles, entities that exist only in periodic bursts, or even offer clues about time's arrow. Why does time flow forward? Could time crystals hint at deeper symmetries hidden in the fabric of reality? Yet the paradox lingers. If time crystals don't consume energy, could they be used to build impossible machines? Not quite. While they defy equilibrium, they can't extract work from their cycles, preserving thermodynamics' grip. But their very existence forces us to rethink what matter can do. Future experiments aim to scale them up, weaving time crystals into networks or probing their behavior near black holes where time itself warps. The discovery whispers a tantalizing truth. The universe's rulebook has pages we've yet to turn. Time crystals aren't just scientific curiosities, they are invitations to explore a world where matter dances to the beat of a different clock, one that never runs down. And in that rhythm, we might just find the next frontier of physics.